You've probably heard people talk about a fast or efficient algorithm for executing a particular task. But what exactly does it mean for an algorithm to be fast or efficient? Well, it's not talking about a measurement in real time, like seconds or minutes. This is because computer hardware and software vary drastically. My program might run slower than yours because I'm running it on an older computer, or because I happen to be playing an online video game at the same time, which is hogging all my memory. Or I might be running my program through different software, which communicates with the machine differently at a low level. It's like comparing apples and oranges. Just because my slower computer takes longer than yours to give back an answer doesn't mean you have the more efficient algorithm. So, since we can't directly compare the runtimes of programs in seconds or minutes, how do we compare two different algorithms, regardless of their hardware or software environment? To create a more uniform way of measuring algorithmic efficiency, computer scientists and mathematicians have devised concepts for measuring the asymptotic complexity of a program, and a notation called Big O notation for describing this. The formal definition is that a function f of x runs on the order of g of x if there exists some x value x naught and some constant c for which f of x is less than or equal to that constant times g of x for all x greater than x naught. But don't be scared away by the formal definition. What does this actually mean in less theoretical terms? Well, it's basically a way of analyzing how fast a program's runtime grows asymptotically. That is, as the size of your inputs increase towards infinity. Say you're sorting an array of size 1000 compared to an array of size 10. How does the runtime of your program grow? For example, imagine counting the number of characters in a string the simplest way, by walking through the whole string, letter by letter, and adding 1 to a counter for each character. This algorithm is said to run in linear time with respect to the number of characters, n, in the string. In short, it runs in big O of n. Why is this? Well, using this approach, the time required to traverse the entire string is proportional to the number of characters. Counting the number of characters in a 20-character string is going to take twice as long as it takes to count the characters in a 10-character string, because you have to look at all the characters, and each character takes the same amount of time to look at. As you increase the number of characters, the runtime will increase linearly with the input length. Now, imagine if you decided the linear time, big O of n, just wasn't fast enough for you. Maybe you're storing huge strings, and you can't afford the extra time it would take to traverse all of their characters, counting one by one. So you decide to try something different. What if you had happened to already store the number of characters in the string, say in a variable called len, early on in the program, before you even stored the very first character in your string? Then all you'd have to do now to find out the string length is check what the value of the variable is. You wouldn't have to look at the string itself at all. And accessing the value of a variable like len is considered an asymptotically constant time operation, or big O of 1. Why is this? Well, remember what asymptotic complexity means. How does the runtime change as the size of your inputs grows? Say you were trying to get the number of characters in a bigger string. Well, it wouldn't matter how big you make the string, even 1,000,000 characters long. All you'd have to do to find the string's length with this approach is to read out the value of the variable len, which you already made. The input length, that is, the length of the string you're trying to find, doesn't affect at all how fast your program runs. This part of your program would run equally fast on a 1-character string and a 1,000-character string, and that's why this program would be referred to as running in constant time with respect to the input size. Of course, there's a drawback. You spend extra memory space on your computer storing the variable, and the extra time it takes you to do the actual storage of the variable. But the point still stands. Finding out how long your string was doesn't depend on the length of the string at all. So it runs in big O of 1, or constant time. This certainly doesn't have to mean that your code runs in one step, but no matter how many steps it is, if it doesn't change with the size of the inputs, it's still asymptotically constant, which we represent as big O of 1. As you can probably guess, there are many different big O runtimes to measure algorithms with. Big O of n squared algorithms are asymptotically slower than big O of n algorithms. That is, as the number of elements n grows, eventually big O of n squared algorithms will take more time than big O of n algorithms to run. This doesn't mean big O of n algorithms always run faster than big O of n squared algorithms, even in the same environment on the same hardware. Maybe for small input sizes, the big O of n squared algorithm might actually work faster. But eventually, as the input size increases towards infinity, the big O of n squared algorithm's runtime will eventually eclipse the runtime of the big O of n algorithm. Just like any quadratic mathematical function will eventually overtake any linear function, no matter how much of a head start the linear function starts off with. If you're working with large amounts of data, algorithms that run in big O of n squared time can really end up slowing down your program. But for small input sizes, you probably won't even notice. Another asymptotic complexity is logarithmic time, big O of log n. An example of an algorithm that runs this quickly is the classic binary search algorithm for finding an element in an already sorted list of elements. If you don't know what binary search does, I'll explain it for you really quickly. Let's say we're looking for the number 3 in this array of integers. It looks at the middle element of the array and asks, is the element I want greater than, equal to, or less than this? If it's equal, then great, you found the element and you're done. If it's greater, then you know the element has to be in the right side of the array, and you can only look at that in the future. And if it's smaller, then you know it has to be in the left side. This process is then repeated with the smaller size array until the correct element is found. This powerful algorithm cuts the array size in half with each operation. So to find an element in a sorted array of size 8, at most log base 2 of 8, or 3 of these operations, checking the middle element, then cutting the array in half, will be required. Whereas an array of size 16 takes log base 2 of 16, or 4 operations. That's only one more operation for a doubled size array. Doubling the size of the array increases the runtime by only one chunk of this code. Again, checking the middle element of the list, then splitting. So it's said to operate in logarithmic time, big O of log n. But wait, you say, doesn't this depend on where in the list the element you're looking for is? What if the first element you look at happens to be the right one? Then it only takes one operation, no matter how big the list is. Well, that's why computer scientists have more terms for asymptotic complexity, which reflect the best case and worst case performances of an algorithm. More properly, the upper and lower bounds on the runtime. In the best case for binary search, our element is right there in the middle, and you get it in constant time, no matter how big the rest of the array is. The symbol used for this is omega, so this algorithm is said to run in omega of 1. In the best case, it finds the element quickly, no matter how big the array is. But in the worst case, it has to perform log of n split checks of the array to find the right element. Worst case upper bounds are referred to with the big O that you already know. So it's big O of log n, but omega of 1. A linear search, by contrast, in which you walk through every element of the array and to find the one you want, is at best omega of 1 time. Again, the first element you want. So it doesn't matter how big the array is. And at worst case, it's the last element in the array. So you have to walk through all n elements in the array to find it, like if you were looking for a 3. So it runs in big O of n time because it's proportional to the number of elements in the array. One more symbol used is theta. This can be used to describe algorithms where the best and worst cases are the same. This is the case in the string length algorithms we talked about earlier. That is, if we store it in a variable before we store the string and access it later in constant time. No matter what number we're storing in that variable, we'll have to look at it. The best case is we look at it and find the length of the string, so omega of 1, or best case constant time. The worst case is we look at it and find the length of the string, so big O of 1, or constant time in worst case. So since the best case and worst cases are the same, this can be said to run in theta of 1 time. In summary, we have good ways to reason about code's efficiency without knowing anything about the real-world time they take to run, which is affected by lots of outside factors, including differing hardware, software, or the specifics of your code. Also, it allows us to reason well about what will happen when the size of the inputs increases. If you're running a big O of n squared algorithm, or worse, a big O of 2 to the nth algorithm, one of the fastest growing types, you'll really start to notice the slowdown when you start working with larger amounts of data. That's asymptotic complexity. Thanks.